So let's do it. Let's just run. And so what I'm going to do, I guess I should show you first. What I'm going to do, oh, I got to go up. I put these solver things in share. Is that up? Yeah, share, settings, solver, LU. Okay, so that function has this in it. And so I have this in solver lu.cfg, right? Please machine run. Okay, so what did it tell you? It told you that there was an error, and it had to do with the solver. And it says there was a 0 pivot in the LU factorization. This means that it found a 0 on the diagonal. It doesn't know what to do. And this happens if you have zeros on the diagonal, as we do with a saddle point system. And so somehow you have to remedy this, right? And so, this failed. It's due to the saddle point. So what I told you, you're like, that doesn't work. And so...
By the way, these .cfg files aren't in the repository.
Why not?
You didn't know.
I thought they were uploaded. Oh, well. Well, they're all...
I believe they're posted on the wiki, though. There is a tarball with the...
Oh, okay. Well, we should just upload them to the... I'll just check them in and upload them. But they're reproduced completely in the slides. So you could, for instance, take the settings that we suggested. These are the settings that we have for most of our examples. So what's happening? We say, well, split the fields into blocks. Okay, split the fields into blocks is to use this blocking strategy. And it just sets a specific matrix type because we lose symmetry when we do this. So I set a maximum number of iterations. I tell it I want to use the field split preconditioner. The use AMAD true means I don't want to use a specific preconditioning matrix to form these things. I'll just use the original matrix. So only for sophisticated things that we do we change that. I say put them together additively means just use this block diagonal type of preconditioning. For the displacement block, let's just do LU again. We know that works. That's what I said to do. And let's do nothing for the fault tractions block. So we can do that. Oh, fault additive. My machine is incredibly slow compared to everyone else's machine. Charles claims it's because the number of tabs I have open in my... So, look, that converges in 58 iterations, which is misspelled, because the preconditioner is just not that strong. It's not a great kind of a strategy to solve two very coupled things as if they are uncoupled. This is what you might do if you were investing and said, these bonds are just not coupled to these other bonds, and I'm going to bet on them, which caused the housing crash, right? So this is not a great strategy. We can do something better. In fact, we can do an exact strategy. Yes?
So is this a GMRes at the outside, or what is that?
Yeah, it's default, so it's GMRes. Yeah. So you could use FGMRes, and it won't change because these are all both linear operators. Yeah. So we can do an exact thing where we have an exact solver, LU, for the displacement, and a basically exact solver for the fault tractions, and we put them together with a full Schur complement factorization I showed you, the big one. So does that work? Do I need to increase the font size? You guys probably can't see this, right? Okay. Okay, so one iterate. And that's how you should be testing. Anything you do with a fault in it, one iterate. If you are not taking one iterate, you are just penalizing yourself. So I'll just go over it precisely here. So, we take one KSP iterate, and I just wrapped a nonlinear solver around this to, in case I want to do these tests with some nonlinearities in there. Nothing in life almost is linear, right? So you can see that you should be able to get this kind of convergence. It's expensive, but this is where you want to be if you're deciding on your physics or your boundary conditions or the kinds of perturbations that you want to make. Once this works and you have a physics result for a tiny thing, then you can start scaling out, okay? So always do this. This should be the default. We'll probably make it the default in PyLith, I think. But let's look now about how to go about changing. So it works in one iterate. This is great. We can do better by weakening. So most of the time in what I just ran is not taken by the direct solve for the displacements. It's taken by the dang solve for the fault tractions, because that Schur complement matrix is not formed precisely. So I have to do all these iterates with GMRes and Jacobi is terrible. So it's like thousands of iterates to solve that thing. So what we can do to accelerate this is have a more intelligent preconditioner for the fault traction part. And so there is one that Brad and Charles and I developed, and it is in PyLith, and you can turn it on with these options. And so whereas initially, here's what we got for the solve that I just ran. If we solve the fault custom PC, fault Schur custom PC. That's why. We can get, we can cut down on those number of iterates from 30, you can save 10 iterates or something like that. If you scale the problem up, you start saving hundreds of iterates. It's just, do you want to wait for my laptop? I encourage you to do it. It's pretty easy to do. How would you, this is the bonus question for more cookies than everyone else. How do you simply test out what I just said? You should not believe me. You should run it yourself. How do you test that the custom preconditioner is going to make a bigger difference when the problem gets bigger? Yeah, it's going to make a bigger difference when the problem gets bigger. How do you test? Do you know? You can do it in one line. So you can tell PyLith to refine the mesh regularly, and you can run again. And then you can plot the number of iterates that it takes as you keep it's in 3D, so you keep multiplying the mesh size by 8. And it's a very easy way. So you can put it in a loop, and you can just keep refining by 8 and plot how much of a difference it makes, and it will make a considerable difference. In fact, we can predict how much of a difference it makes because we know what the condition number is, and we know how that cruddy solver behaves as a function of condition number. So you can, so I got a working thing that I'm pretty happy with that takes one iterate on the outside, but it relies on this very accurate solver for the Schur complement that's taking a long time, right? So what do? Well, we can make it less accurate. So what happens if I make the block solve less accurate? If I make the block solve less accurate, then the outer solve needs to do more work. And so this is what happens. So let's just do this, right? And the way you do it, so you can stick everything in the file, but I tend to, if I'm playing around, right, I don't want to take the time to do that. So I just do a bunch of stuff on the command line, and then when I'm happy with it on the command line, then you can stick it in the file, right? Just file editing is a pain. Okay, so what did I do? I said, okay, let's not solve the fault traction block to 10 to the minus 11. Let's solve it to 10 to the minus 5. Okay, if I do that, it doesn't look linear anymore. It looks nonlinear because it's a different kind of solve each time. So I need to change to FGMRes on the outside. Okay, so what happened? What happened is I used to take one iterate on the outside. Now I take two. But the inner iterates I take are 10 and 15 instead of 24 and 25. So overall, I win. And these are the kind of subtle trade-offs that are involved in optimizing your solves. Yes?
Can you show what happens when you use GMIs?
Sure. I'm not sure how much of a difference it makes, so this will be interesting. My guess is that it's going to converge a little bit slower, but no, not that. Oh, well, okay, so it's a little bit of a fake because, okay, I'll show you. FGMRes cannot calculate the preconditioned residual very efficiently, so to make them exactly the same, KSP, PC side equal right. I think that's right, right? Guess I could check it. No, I didn't give the right one, but it converges about the same. So there isn't any difference here, but you should use it because if you get bigger, like sometimes they'll come out. Like we should refine and check. So you can do that kind of backing off where you say, I want to solve something I was previously solving to very high accuracy, now I'm going to back off. Now, there's a real difference between solving subproblems to low accuracy and solving the full problem to low accuracy that I want to point out here. Here, I've said, I'm going to solve a subproblem to lower accuracy, but the full problem I'm still solving to the tolerance that I need. I'd be very wary of backing off the full problem tolerance unless you have a very good idea what you need, to get your results. And if you're talking about new physics, I don't think it's safe to solve to anything but kind of very high tolerances. Now, I know people do different things, and they're happy with it, but I wouldn't be. Another thing we can do is we can say, instead of doing direct factorizations, why don't we put multigrid in? So I can do that too. And again, I'm just going to do it from the command line because, I didn't want to make a million files. Oh, I should have put minus Petsy dot. So what does this do? This says, okay, instead of doing LU, I'm going to do algebraic multigrid. And this is for the displacement block. So when we had an inexact solve for the fault tractions block, we lost an iterate, but it wasn't so bad. But here, inexact solves for the momentum block are much more damaging, right? So instead of 2 iterates, I'm now taking 7. And in fact, it took me an extra 1 to get the nonlinear tolerance down because, oh, really? That's not right.
You're still using GMRS?
Yeah, that's what it is. I can't kill it? There we go. Nope. Yeah, it's determined. Okay, hold on. Oh, I can't easily switch with PSAUX, www pipe grep MPI. Kill -9. Oh, there's like another MPI job lurking there too. Okay, there we go. Yeah, so you really don't want to do GMRes when you're doing this stuff. And that's an example of why, I think. Yeah, so that's exactly what I was talking about, and this is a good example. So what happened? Why did it go wrong? What happened was that I had a nonlinear preconditioner, a preconditioner that was not the action of a linear operator. GMRes anticipates a linear system, and it makes, it gets a set of vectors and solves a small linear problem. If the problem is actually nonlinear, it can get a very small residual, but the error is big. And so that's why I always wrap the nonlinear solver around the linear solver. If I just had a linear solver, it would have said, I am solved. But I violated one of the assumptions in the Krylov method, and so it showed a residual that was much smaller than it actually should have been. And so checking on the outside with a nonlinear solver is a very good thing to do. And here you can see we solved it in one iterate, right? Yep. So I always recommend doing that for just to have this kind of check. But you see that we lost a bunch, right? We're doing a lot more inner iterates than the 40 or so that we had been doing. Now, they're less expensive and they're more scalable and whatnot, but probably you're going to lose in this scenario if you just did that. However, what this should be telling us is inexact solves for the momentum block have a high penalty. So maybe what we could do is we could do something more scalable than LU, but still get a higher precision solve. So right now, I've just done algebraic multigrid. What if I did algebraic multigrid coupled with a Krylov method on there instead? Yes?
So it's just one V cycle?
Yeah, I just did one V cycle, just to show, you know. And so that's why it's got pre only there. Yeah. And so what you can do is you can add in GMRes to this mix. Instead of doing pre only here, I can say, let's do GMRes. And I don't have to do a lot of it. So I can just do, what do I have here? Oh, well, okay, that's a pretty low tolerance actually. So I'm going to be pretty accurate, and you can mess around with things like this. I think you could probably back off this tolerance and still do pretty well. But I just want to show you. It's not many iterates. Yeah, and it's back down to 2. So with an accurate solve, I can get to wherever I want to be in terms of the trade-off space. Yep, and that's what I have on the slide here. So these are the kind of manipulations that you want to think about doing. Start with something that is guaranteed to solve your problem, and then in steps, look at the performance, decide which part is really limiting you, back off the part that's limiting you. The problem with this simple example is I wanted to run in 5 seconds, so looking at the performance is sort of meaningless. But what I would do for a real problem that took like 10 minutes to run is I would look at the log summary like I showed you, and I would see which pieces of the solve are taking the most time. And then I would try, I mean, of course it's connected, because you could say, oh, this piece of the solve is taking a long time, but it's causing very few iterates. So if I back off that, then the iterates go up. So it's not totally easy. But these are the kinds of things. So I wanted to show you an example of, hey, I have something. I'm going to go from very robust to pretty robust, more performant. Yeah.
What do you think is the best strategy to aim for? Is it like the outer iterations should be in the ballpark 10?
Yeah.
Or is it balance inner and outer work somehow?
I think it's the outer iterations should be in the ballpark 10. in my opinion, because you really should only be using outer iterations to clean up stuff that the inner thing missed, and 10 is like a pretty good target for these are the eigenvalues that I haven't handled correctly. I don't like having a lot more than that number of outer iterations, and usually by messing around with algebraic multigrid or making the Schur solver more powerful, you can get down to that neighborhood.
But going to 1 or 2 is probably...
That's probably overkill. Yeah, I'm just overkilling everything here just so I can show, you know, the effect. But it's usually a much more subtle effect, like from, you know, 15 to 8 or something like that. Not that bad.